Hello, class. Welcome back to the spring semester. Um, I would like to talk to you about MEC 131 statics. Just to let you know, my name is Ed Morris, and I have been teaching for quite a while, especially statics. I taught engineering courses at Tidewater Community College for over 6 years. I've also have taught engineering courses at Thomas Nelson. I'm actually the CAD program head at Thomas Nelson and the dual enrollment machining program head. But I do teach engineering courses from time to time, and they've asked me to teach this one. Normally, Professor Young teaches this class, and she's an outstanding professor. And I was honored that she asked me to fill in for her since she had a significant workload last semester, and she has one this semester as well. Anyway, so I'm in a Canvas, so I would like for you to open up this link, Meet Your Professor, and you can learn more about me. So I'll just open up real quickly here. I'm not going to read all this to you. It tells you all the classes I've taught, where I have worked at as an engineer and as a professor, and just some things about education in general and also engineering. Okay. Also, the syllabus is here. I'm not going to read all this to you because you know how to read, but I do want to highlight some things real quick. Please read over the course description. The prerequisite is Math 162 or 164 or Math 167 or Math 166. Please read over the general core competencies. Again, my name is Ed Morris. This is my email address right here. Also, this is my telephone number, 825-3624. Later on, I will give you my personal cell phone number. That way you can text me or call me on my personal phone. Again, read over a lot of these objectives. I'm not going to read all this to you. I'm going to get right to the chase here. Your textbook here, this is your textbook. It is in the bookstore, and if you want to purchase it, you can. It's an older book, so you might be able to rent it. So there's other ways of being able to obtain this book. But anyway, do your best to get this book if you can. If not, maybe perhaps you can share with one of your friends in the class. That is totally up to you. But you should have no trouble finding this book. Again, it's an older book. So I would go online and see if I could find a used one. Make sure you have a scientific calculator. Make sure you know how to access Canvas. Okay. Here are some important college dates. I will go over these with you. The last day to add or change a class is January 15th. Last day to drop for a full refund is January 27th. And the last day to drop with a grade of W is March 24th. Okay. Spring break occurs from March the 7th till March the 12th this year. And also April the 30th is the last day of class. Okay. And then exams will be from May the 2nd until May the 7th. And then the grades have to be submitted and SIS by May the 10th. This is probably the most important thing to talk about here is tests will count 60%, quizzes 20%, and final exam 20%. The test, I don't know, they'll be between 3 or 4. I didn't give you the exact number because it depends on things. So we'll see how we progress in the class. Now, again, you will not have more than 4 tests as far as tests are concerned. Homework, if you do your homework, that will help you on your quizzes. And then the final exam, you have a final exam. Grading, 90 to 100 is A, 80 to 89 is a B, 70 to 79 is a C, 60 to 69 is a D, and below 60 is an F. Please read over all the college policies here. I'm not going to read all this to you, but obviously we don't have to worry about children in the classroom, but I am going to have some help sessions periodically. And if I do, I love children, but please mute your computer, or perhaps just have them be quiet for just a little while as we get through the lecture, and then just want to respect everybody here, both your classmates and your professor. Don't worry about being late here, obviously, right? Because it's an asynchronous course. So you take the class whatever time that's convenient for you. However, we still have to meet deadlines, okay? All right, so just read through the rest of this. All this is pretty much just some of the policies at Thomas Nelson Community College. If you have any questions or concern about any of these policies, please make sure you contact me. Okay, thank you. All right, now let's go back to modules here. This is a schedule that Professor Young put together. She has all the credit here for putting this together. I will do my very best to stick to this schedule, but notice it says tentative, so things can interrupt our schedule. We'll do our best. We'll see how we progress, okay? I know it says quiz 1, quiz 2, but that might be bumped to the following week. It just depends on how we progress in the class, all right? So we will do our best to try to stick to this schedule, okay? And let's see. Now, here is a PowerPoint on dimensions and units of measure, and I would like to give credit where credit is due. I had borrowed this information from my good friend and colleague, Paul Gordy, at Tidewater Community College. Some information is stuff that he put in there, so he gets full credit, and there's some information that I put in there. And I'm not going to go over all this. I want to go over some of this with you. A unit of measure is a predetermined reference amount that is used to help us understand the magnitude of a physical quantity. Magnitude means size, okay? Dimension is a term used to describe a physical quantity, such as length, temperature, time, etc. Dimensions can be described using various units, right? You can use inches and meters, millimeters, and so forth. So length is a dimension, and a dimension could be 0.833 feet, or it could be 10 inches, or 25.4 centimeters. And by the way, all of these are equal, right? There are two systems. There's the SI system and the English system of units. One of the advantages of the SI system is everything is based on the units of 10. And by the way, as we go through this PowerPoint, you'll see some areas where I want to do some conversions a little bit later. I'm not going to do them today. And feel free to, for yourself to practice doing some of these conversions, because it's very important that you know how to. You always want to make sure you don't want to mix apples and oranges, okay? You have to be consistent with your units. There is one equation that we're going to focus on a lot in this class, and also you will see this equation more so in dynamics, called Newton's second law, with force equals mass times acceleration. And the interesting thing about this equation is most things are dependent upon mass and not force. So, for example, if you weigh 180 pounds on Earth, that's your weight. You're going to weigh 30 pounds on the moon, because the acceleration due to gravity is 1/6 of that on Earth. So your weight will be less. So when you're designing something for space or on Earth, a lot of times, especially NASA, will use the mass and not the weight of the components. Here's an example. So suppose you are an engineer working for NASA and you are providing specifications for a part on the space shuttle. Well, we no longer have space shuttle, but maybe one day we'll have a new fleet of shuttles. Which of the following two choices would you take? Specify its weight. If you specify its weight, if its weight is 100 pounds on Earth, then it weighs only about 17 pounds on the moon. And its weight is approximately 0 in space. So that's not a good choice to select weight. However, if you specify its mass, If the mass is 100 kilograms on Earth, then it's also 100 kilograms on the moon. This is a much better choice to use, is the mass. The SI system is a worldwide system. However, in the United States, we use both. We're hesitant about using just the SI system by itself. There was a lot of resistance back in the 70s to changing over to completely over to the SI system. So here's some things I'd like to go over with you here real quickly. In the early 70s, again, the United States attempted to switch fully to the SI system. Even speed limit signs were put up in kilometers per hour. I remember that. I was a kid, and they had both miles per hour and kilometers. Of course, they took them back down. Speedometers on cars show both. Even today, the cars show, miles per hour, right, and kilometers per hour. Schools also began teaching the SI system back in those days. A very good textbook that they use for statics is Beer and Johnston, which is a good book. It's a good reference book for this class. It's more calculus based. I will mention that though. But anyway, they also fully switched over to the SI system, but unfortunately, some special interest groups back in the 70s put a brick wall up with this. They were resistant to the change, so we never fully converted over to the SI system, so we use both the SI and the English system. So, and Beer and Johnson, again, the textbook I was talking to you about, 50% of their problems in the textbook are SI type problems, metric system, and then the other is English. Okay. Canada. Now, my friend Paul Gordy, he had a student who came from Canada, and he never learned the English system. All he knew was SI system. So he came to the United States, and he took the statics class with my good friend and colleague Paul Gordy, and he struggled a little bit because he didn't know the the U.S. English system. So he did struggle with that somewhat. So there is hope that we will one day convert to the SI system fully. And back in 1992, the federal government did require all engineering work that was done on federal facilities to use SI system. And this had a positive effect with the construction of the buildings, design of the buildings, the plumbing, the electrical, HVAC system, landscaping, all had to be using the metric system or the SI system. Here's a good article that you can read at your leisure, but it tells you about when, back in 1992, that all federal agencies were going to adopt the SI system. Here's a good article that you can read that talks about because using getting the metric system mixed up with the English system, there was one of these orbiters crashed into Mars back in 1999 because of the mix-up with the units. Now, the SI system is the base units for the SI system, and sometimes you hear metric system. And the metric system is a part of the SI system. The length is a meter, that's the base unit, and the symbol is lowercase m. Mass is kilograms, so the symbol is kg. Now, time is the same for both English and metric, obviously. So that's has the symbol lowercase s. Electric current, ampere is the uppercase letter A. Thermodynamic temperature is Kelvin. The amount of substance is a mole. And luminous intensity is candela. Now, earlier we were talking about Newton's second law. Here's the equation right here. Okay, I want you to notice something. The mass right there always has to be in kilograms. Always. The mass always has to be in kilograms. The acceleration has to be converted to meters per second squared. So a kilogram times meter per second squared is a Newton. You may have heard the name Sir Isaac Newton. Sorry, long day. Sir Isaac Newton is the force is named after him. Okay. Again, here are the definitions of the length, which is a meter. Time is second. And these are the base units, right? Mass is kilogram. Electric current is ampere. Temperature is Kelvin. Amount of substance is the mole. And luminous intensity is candela. Make sure you read through these definitions, okay? You won't be responsible for this, but please read through it. Here's another good article if you have a chance to read through this. Let's see. Okay, so prefixes. So you hear the term kilogram, okay? So this is the prefix kilo, which means 1,000, right? 10 to the plus 3. And hecto means 100, so that's 10 to the 2. And deca means 10, that's 10 to the 1. A decimeter, right? That's 1/10 of a meter. Centimeter is 1/100th of a meter. Millimeter is 1/1000th of a meter. Micrometer is not micrometer, micrometer is 10 to the minus 6. Nanometer, you've probably heard that before, 10 to the negative 9. Now, some of these other ones you may not have heard, like pico and femto, and you don't hear these too often. But you do hear of nano, right? So you have heard probably this prefix, nano. And giga, that's 10 to the 9th. I'm sure you've heard that. Mega, 10 to the 6th. So be familiar with these prefixes, okay? And they will not be on test 1. This is from an older class, so you don't have to worry about that. When you're making a table of values, for example, you want to keep all your units consistent. Notice this is newtons, this is kilonewtons. This would be a better way to lay this out, is to make everything in kilonewtons, okay? So notice, again, this is newtons, kilonewtons, meganewtons, right? So it's best just to put it all in kilonewtons. Some abbreviations that you're familiar with, but you may not pay much attention to this too often, but when you write 10 seconds, you don't write 10 seconds like this. You don't write 10 seconds like this, okay? You write 10 seconds like this. So time is 10 seconds. You don't write it out like this, okay? This is not a unit. This is a unit. Same thing with electrical current. Amp, you write 15, and then the uppercase A, you don't write it out like this, okay? Also, like with pounds, a lot of times we think we're supposed to put a period here, right? Well, you don't. You just write it out as 10 pounds without a period, and no comma either. So it's just 10 pounds. And you don't make it plural like this. It's not plural. This is the way it should be written out. That's the correct way of doing it. So there's some other units that we're not going to cover right away, but you have Pascal for pressure, and Hertz, and Newtons, again, from Sir Isaac Newton. These are all from a proper name, someone's name. Pascal. I'll let you look up these names in Hertz. Okay, these are names of scientists, right, from the past. Again, time is not a person's name, right? So this is 10 milliseconds right here. 10 milliseconds. Anyway, I do want to show you this one calculation here, though, where someone was calculating the amount of force, and these were the units that were given right here for force, or to calculate force. This is gigagram. So that's going to be 10 to the 9th right there, right? 6 times 10 to the 9th. That's a giga. And 8.50 centimeters per second squared. I want you to notice something. They converted the gigagrams to 10 to the 9th grams. See? 6.00 times 10 to the ninth grams, and then times the acceleration, but they noticed they converted it to what? Meters per second squared. So if you don't get anything out of this lecture today, remember this: your mass has to be in kilograms and your acceleration has to be in meters per second squared when you're using Newton's second law. Okay? One more time: mass in kilograms and acceleration has to be in meters per second squared. And that's what they did. They converted to the proper unit. Say they converted to kilograms, okay, and then they converted to meters per second squared, and then they got newtons, okay. Here's some more conversions I'm going to probably do with you later on, not today. Some English units that you're very, very familiar with, right, is feet and seconds and pounds. Again, notice there's no S with pounds, right? It's just lowercase l and then b. Now, in the SI system, mass is in kilograms, but in the English system, mass is in slugs. So we don't use kilograms in the English system, obviously. We use slug. So this is what a slug is defined as: 1 pound times second squared divided by feet. Okay? That's what a slug is. So slug is a derived unit. And there's the definition for one slug is equal to 1 pound per second. Not per second, is 1 pound second squared divided by feet. Okay, you can read through most of this. I'm just hitting some highlights here. There is some more conversions I'm going to do for you eventually. I do want to point out that you do have some good online conversion programs that you can use. One is called Digital Dutch here, and you can convert from one system of units to another. There's quite a few out there on the internet, but sometimes you need to know how to do these by hand as well. We're going to do some of the easier ones in class by hand, but some of the more difficult ones you don't maybe not have time to figure out. You can just use a unit converter. All right, I went through this rather quickly. I am going to go back and do some of these conversions a little bit later on. Some of this is more related to other classes, not so much statics, but you really need to understand the importance of units. You really do need to understand the importance of units. You can't mix and match. You can't really mix the English system with the metric system. You can't really combine them. Now, there is an advantage of using the metric system, right? Everything is based on units of 10, which makes it much easier, right? Okay, so let's go back to the module. Now, the next PowerPoint is a little bit quicker. So we're going to talk about significant figures, okay? Now, before we can talk about significant figures, we have to talk about precision. What is precision? Precision refers to how close together a series of measurements are to each other. For example, here we have the famous example of the dartboard. Here you have 4 of the darts close together. These are precise as far as the location of the darts, but they're not accurate because they're not actually at the bullseye. Okay, so they're precise but not accurate. Accuracy, though, refers to how close a measured value is to an accepted value. So here we have the darts at the bullseye, which means they're precise because all the 4 arrows are darts are together, and they're also accurate because all of them are in the what? At the bullseye. Now, in this particular example, they're not precise and they're not accurate. The darts are not close together at all, right? And none of them have what? None of them hit the bullseye, okay? So this is an example of not precise and not accurate. Here's an example of a man. He's on the scales weighing himself. He says his actual weight is 250 pounds, right? Well, look at these weights here. None of these come close to 250 pounds. The closest one is 230, which is a 20-pound difference. So these are not accurate, nor are they precise. Okay. Now over here, they're precise because the weights are fairly close to each other, like 240, 239, 238, 241. They're close, but they're still not accurate because he weighs 250 pounds. The closest one is only 10 pounds difference, right? Now, over here, all the weights are fairly close to one another, like with 1 or 2 pounds, and they're accurate because they're very close to his weight of 250 pounds. Now we need to talk about significant figures. Perhaps you've had a chemistry class or a physics class where you need to learn about significant figures. The use of significant digits in expressing measured quantities gives us the ability to indicate the intended degree of precision. A different degree of precision is implied by saying, okay, 5 gallons of water versus 5.000 gallons of water. There's a difference. Okay. Now, there are 3 basic rules for significant digits. One of them, here's an example: all non-zero digits are significant. So, for example, this number has no zeros in it, right? So all 4 of these numbers here count. So there's 4 significant digits that make up this number here. There's no zeros here. Now, all leading zeros are not significant. So like for this one, 0.003, you have leading zeros. They're not significant. The only number that's significant is the 3, or the only digit that's significant. So therefore, there's only one significant digit here. Trailing zeros, okay, so this number has a trailing 0, right? Now you do have a decimal here. It says trailing zeros are significant, except with the whole numbers where their significance may be uncertain. And we're going to look at some examples that's going to help us understand this much better. Okay, let's look at this. Do you see any zeros here? All non-zero numbers are significant. All non-zero numbers are significant. So we don't see any zeros here. So we got 1, 2, 3 significant figures. So that's 72.3 grams. So that's 3. Here we have 3 as well, significant figures. And here we have 2, 25 pounds. Notice there's no S with pounds, right? All right, it's just LB. Okay, talking about the units earlier. Here we have captive zeros. So they do captive zeros are significant and do count. So you have 2 zeros here, but they're going to count. So we have 4 significant digits right here, 4 of them. Okay. So this measurement has 4 significant figures. This one also has 4, and this one has 3. Okay. All right. If a number has a decimal point, like this one, the trailing zeros are significant. If you have a decimal like this, the trailing zeros are significant. So you have 3 here, 3 significant figures. You have 4 here, and you have 3 here. Okay? If the number has no decimal point, which these numbers do not, then the trailing zeros are not significant and do not count. So here, these trailing zeros do not count. We only have 2 significant figures. These 3 zeros here do not count, so we only have 2 significant figures. Here we only have 2 significant figures as well. Okay? Leading zeros in a number are not significant. You have leading zeros here. Okay, leading zeros here. So they are not significant. Okay, so only these two numbers are significant here. Right here, these leading zeros here are not significant, so we have 4 significant figures here, and then this one here, these 2 zeros here do not count, so you only have 1 significant figure here as well. All right, now this is something I saw on the internet a while back, and I thought it was pretty cool. You have what they call the Atlantic side and the Pacific side. If it's the Atlantic side, there's the decimal is absent. Okay, there's no decimal. If it's the Pacific side, there is a decimal present. So decimal, no decimal. So what does this mean, Mr. Morris? Okay, here we go. So if you're coming from the Atlantic side, it says if a decimal is absent, no decimal, start counting from the Atlantic side, from the right, right? You start counting this way. Skip over any zeros and begin with the first non-zero digit, okay? So this is the first non-zero digit. I mean, this is the first non-zero. So these don't count, so you have 3 significant figures, okay? So these 2 zeros don't count. There's no decimal present, so 3 significant figures. So coming from the Atlantic side, these coming from the right, moving to the left, these don't count, so you got 1 significant figure. These 2 zeros don't count, so you have 2 significant figures. These 5 zeros don't count, so you have 1 significant figure. In this case, you have captive zeros, so you have a 2 here and a 1 here, so these are all significant here, so this is 5. Now you don't count here, coming from the Atlantic side, these 5 zeros don't count, so you have 2 significant figures here, and these 2 zeros here don't count, so these are 4 significant figures here. Remember, they don't have no decimal, so you start counting from the right side, moving left, and you stop at the first non-zero number, okay? And that's when you start counting. Here on the Pacific side, right, it has a decimal is what? Present. Is present. Skip over any zeros, so skip over these, and begin counting with the first non-zero digit here. So 1, 2, 3. So you have 3 significant figures here. So this has a decimal. Pay close attention now. This has a decimal, so there's 3 significant figures. This has a decimal here, so there's 4 significant figures. Because this is the first number coming from the Pacific side, we're moving from left to right. This is a non-zero number, so 3 significant figures. This is a non-zero, 4 significant figures. The decimal is present. This is your first non-zero number. All these numbers, 4 significant figures here. You have a decimal here, right? You have a decimal here, but your first non-zero number is a 7. So you got 1 significant figure here. You have 2 significant figures here, right? You don't count the zeros, and then you have your first non-zero number is 1, so all of these count. So this is 5 significant figures. When you're doing math, when you take 2 significant figures and you divide by 2 other significant figures, after rounding, which we did here, we rounded off, we have 2 significant figures here, okay? So this is division. You have 3 significant figures divided by 3 significant figures. Your answer must be 3 significant figures after rounding. So this 8 becomes a 9. Okay, so 3 significant figures. 4 significant figures divided by 4 significant figures after rounding. You use the first 4 significant figures. Okay. Multiplication, 2 significant figures times 2 significant figures is not 4 significant figures. This is the right answer, right? But when you're worried about significant figures, then you're going to round up. You're going to round up here, so the 5 becomes a 6, and you only have 2 significant figures here. Because remember, the trailing zeros don't count, so it's 1600. Here you have 4 significant figures times 4 significant figures. Here you actually have 7 significant figures. So this is not going to be correct. It is the right answer mathematically, but as far as significant figures go, you're going to have to, after rounding, so make these trailing zeros. So these are 4 significant figures right here. These 3 zeros won't count. Okay? And adding, you take the number with the lowest number of decimal places, which is this one. You're only as accurate. You're only as accurate as 1 decimal place. So you're, after rounding, you have 1 decimal place. 1 decimal place here. So after rounding, 1 decimal place here. You're only as accurate as your as 1 decimal place. Same here, 1 decimal place. So after rounding, 1 decimal place here. No decimal places here, so we can't have any decimal places here. Okay. With subtraction, we had 4 significant figures here and 6 significant figures here, right? But your final result can only be 2 significant figures, 4, because this is 4. Okay, it can't be 6, it has to be 4 after rounding. So they actually round that 3 to a 4. Some more practice. Okay, so you got 12, 0, 1, 2, 0, 0, 1, 2. So this is 2 significant figures, 2 significant figures, 2 significant figures, because you have leading zeros. Here you have trailing zeros. So you have 2 significant figures here, 2 here, but hang on, right here you got a decimal. Be careful with that. So that's going to be 4 significant figures. Over here you have captive zeros, that's 4. Over here, the trailing zero is not included, so you have 4 significant digits. Here you have a decimal. You do have to include that last digit, which is 0. So you have 5 significant figures there. The way to work around this is to use scientific notation. Okay, so in other words, like for example, 4,000 here, that has only 1 significant digit when you write it this way. However, when you write it in terms of scientific notation this way, then it's 4 significant figures. So that's 4 times 10 to the third. So that's 4. This means the same as this, but this is more accurate, right, and more precise. So you have 1 significant figure here, 2 significant figures here, 3 significant figures here, 4 significant figures here, and 5 significant figures here. I keep saying figures, but you can say figures or digits. Thank you. So that completes the information on units and significant figures. So I will be posting this video soon. Thank you.